Okay, thank you. So I will start with a very brief self-introduction. So I came to Japan more than 20 years ago and spent all my career in Japan. So I speak Japanese. Actually, 2 years ago, I gave a similar talk at the Q2B in Japanese, but today I will do it in English. And I'm working mainly in the field of theoretical computer science, especially the theoretical analysis of quantum algorithms and the quantum complexity theory. And the topic of this talk will be quantum advantage. So first of all, we know that small-scale quantum computers can perform computation faster than classical computers. A famous example is Google's quantum supremacy experiment 2019. So the task considered there is to compute the output of a random quantum circuit acting on 53 qubits. And there have been several further works in that direction, but they all share the same flavor. So they all start with a computational task that can be solved on a small-scale quantum device and show that the task cannot be solved efficiently by a classical computer. But the very important point here is that the quantum algorithm involved in proving these experimental quantum advantages are not really solving useful computational tasks. They are only solving tasks that cannot be solved by classical computers. And in this talk, I will focus on understanding whether we can design whether quantum computers can perform useful computation faster than classical computers. And there are a lot of works in that direction, and they can be roughly divided in two categories. On the left, quantum algorithm with probable advantage over classical computers. So many examples: integer factoring, so Shor algorithm; quantum search, the Grover algorithm; quantum simulation; and more recent topics like quantum distributed computing. And the point is that for those cases, we have theoretical guarantees of the quantum advantage. But the main problem is that all these algorithms typically require quantum error correction. So we cannot really implement without fault-tolerant quantum computers. On the right, we have heuristic quantum algorithms, many very exciting and powerful techniques. The very nice thing is that, to some extent, they can be implemented on current devices. But the main issue is that generally we don't have very strong theoretical guarantee of the quantum advantage here. And this talk will be about quantum algorithm with probable advantage. And I've been working on this topic for essentially all of my career. So I studied a lot of different areas of a quantum algorithm with probable advantage. And today I will present my own selection of my favorite examples of quantum algorithm with quantum advantage. So all those mentioned in this slide. And I will start with this one, so matrix multiplication, quantum algorithm for matrix multiplication. Okay, so matrix multiplication is really one of the most fundamental computational tasks in science and engineering. So the basic setting is I give you two n by n matrices, and I ask you to compute the product. So the trivial algorithm simply uses a formula, definition of matrix multiplication. So you want to compute n square entries. For each entry, you can use that formula. So it's essentially linear number of operations. So in total, a cubic number of operations. If you use very clever techniques, you can improve the exponent down to 2.38, but this is really the limitation of current classical algorithm for dense matrix multiplication. And a few years ago, we started considering quantum algorithm for matrix multiplication. And here I represent the complexity of the algorithm we designed. So the horizontal axis represent, the horizontal axis represent the sparsity of the output matrix. So the parameter we consider here is the sparsity of the output matrix, the number of non-zero entries in the output matrix, so between 0 and n squared. And the vertical axis represents the complexity in log scale. So you can see that if the matrices are extremely dense in this region, you don't get any advantage. But if the output matrices are reasonably sparse, then you do get an advantage. And for example, if the sparsity is n, so we have about n non-zero entries, which means that we have roughly a constant number of non-zero entries per row or column, then you have a huge advantage, quantum advantage here, the classical complexity and the quantum complexity. And the point is that such kind of sparse matrices appear a lot in graph algorithms. So using those algorithms, quantum algorithms, you can obtain fast quantum algorithm for many tasks in graph, for many graph problems. This is the first example of provable quantum advantage. I will now move to the second one, which is slightly related because it's related to another very fundamental problem in linear algebra, which is solving a system of linear equations. Okay, so it's a HHL algorithm. As an input, we have one matrix, n by n matrix, satisfying some technical conditions, should be sparse and well conditioned, but it's not very so important. And you have one vector, norm1 vector, also dimension n. And a vector of norm1 can be seen as a quantum state. So we assume that it is given to the quantum computer as a quantum state. Okay, and now consider the solution of this system of linear equation, Ax equals b. The solution is this, A inverse applied to B. And we normalize it. We divide it by the norm, so you get the vector of norm 1. And the vector of norm 1 is the quantum state. So the task we want to solve is to output an approximation of that normalized solution to the system, this quantum state. And Arrow Archimedes law, I've shown that this can be done in time polynomial in log n, the logarithmic of the dimension. And in comparison, classically, solving a system of linear equation requires linear times if you want to do it with good precision for such well-conditioned and sparse matrices. So you get a huge advantage between the performance of classical and quantum algorithm. You get an exponential advantage here. It's a very impressive result. But there is one issue. The issue is that the solution of the quantum algorithm is also a quantum state. Okay? And typically, this is not really what we want. When we want to solve a system of equation, we want to have all the coordinates of the solution. Typically, having a solution as a quantum state is not enough. But there are many potential applications to this algorithm. For example, estimating some statistics about the solution. And concretely, such kind of application have been suggested to quantum machine learning. There are several papers using the HHL algorithm to obtain fast algorithm for machine learning. This is indeed a very promising field, but it's fairly difficult to analyze the performance of those quantum machine learning algorithms. Why? Because in machine learning, typically, we don't have a good theoretical understanding of the performance of algorithm. What we do, we need to run the algorithm on real data in order to analyze the performance. And if you want to do it for quantum machine learning algorithm, it's problematic because we don't have a large scale. We don't have yet a large scale quantum computers. Okay? There are still some theoretical investigation possible for some specific quantum machine algorithms. So for example, recommendation system. There was a quantum algorithm for solving this the recommendation system problem faster than the best known classical algorithm at this, when the algorithm was created. But the point is that most of this quantum algorithm, where we have a rigorous analysis, have been actually dequantized. So I've been able to show that actually for essentially all these examples, you can achieve similar performances with classical computers. Okay, so we are in a situation where quantum machine learning and application of the HHL algorithm seems very promising, but we are still missing a killer application. Okay, so now I will move to the next one, which is quantum simulation, especially computational quantum chemistry. So computing the ground energy of a quantum system is a very fundamental problem, but it is very hard. It's known to be hard even for quantum computers. But the point is that given a rough approximation of the ground state, you can do it. You can estimate the ground energy with high precision on a quantum computer by using phase estimation. Okay? And the point is that in many applications, like quantum chemistry, we do know how to get a rough approximation of the ground state. There are many techniques, so for example, the Hartree-Fock technique. So you first apply these techniques to get a rough approximation of the ground state, and then you apply phase estimation, and you can get a good approximation of the ground energy of the system. So that's why this is very promising application of quantum computers. But until recently, there was no mathematical proof of a quantum advantage here. And what I've done with a few collaborators is to prove mathematically that this task here, solved by a quantum computer efficiently, is actually hard for classical computers. We have shown that computing the ground energy with high precision is hard with classical computers. Okay? So this really shows that for this fundamental problem, you have a probable quantum advantage, which is actually exponential. And we have also been able to show that actually computing the energy with constant precision, it's easy even on a classical computer. So the combination of these two results really show that the superiority of quantum algorithm comes from the improved precision that you can obtain. Okay? Constant precision, you can do it classically efficiently, but inverse polynomial precision or high precision, we can do it on a quantum computer, but it can show that it cannot be done on a classical computer. And there are some computational complexity assumptions. Okay, so another topic that I think is very important is quantum optimization. Okay, so quantum optimization, there have been in this conference many talks about quantum optimization. There are several, again, categories of quantum algorithm for optimization, those with theoretical guarantee and those which are more heuristic. But there is another field in optimization theory, which is convex optimization. And convex optimization, especially the study of linear programming, linear programs, and semi-definite programs, has a wide range of applications, rigorous guarantees, and can be solved efficiently by classical solvers. So they are used a lot in practice and can solve a very large optimization problem very efficiently. Okay. And here in this slide, I show the theoretical analysis of the performance of the best classical algorithm for solving semi-definite programs. So the complexity is written here. So this term and this term. So n is the number of variables, and epsilon the precision of the solution. And there have been, in the past 10 years, several works investigating quantum algorithm for this task. So I mentioned only a few of them there. There are more, but I cannot write it due to space constraints. And the point is that if you see the dependence in n, the dependence in n is significantly improved from 2.5, exponent 2.5 to exponent 1/2. But the dependence in the precision is much worse. Okay, so you get polynomial in 1/epsilon instead of polynomial in the log of 1 over epsilon. But this means that you still get a significant improvement if you are okay with low precision. Okay, so if you don't care much about the precision, you get a huge improvement here. And I've talked with several experts in optimal optimization. They are really excited by this because they really want to solve very huge optimization problem with millions of variables. And having complexity like this, an exponent 2.5, is really make the algorithm intractable. Okay, and they are very excited in the possibility to have an algorithm working with dependence quadratic in the parameter n. So I really think this is this quantum algorithm for SDP may be the only way to get an approximation of SDPs when the number of variables is very, very large. So it's really, in my opinion, a field with a potentially very wide impact. Okay, and finally, I would like to discuss a little bit the quantum string algorithm. So the problem, one of the basic problems in this field is I give you two strings, and I want to compute their similarity. So for example, the strings can be files, and you want to compare the two files, or they can be DNA, and you want to compare the DNA. And of course, we can ask how to define the similarity. There's many possible definitions, but here I will consider one of the simplest, the length of the longest common substring of the two strings. And the point is that for application, the strings are very long. For example, if you consider DNA, the length is billions, 3 billion, something like that. So you really want to design fast algorithm. So classically, it's known that you can solve it in linear time, and you can also show that this is optimal. The argument is very easy. You can really show that you really need to go through all the input in order to estimate the similarity. But the point is that recently we have been able to construct quantum algorithm with complexity sublinear. Okay, so the complexity is n to the power 5 over 6. It has been recently improved to 2 over 3. And if you compare to it, since I said that classically you can show that you need linear time, this gives you a proved advantage. And this is, I believe, a new topic in quantum algorithms, and there are several works in the past 2 years on further quantum algorithms for other string algorithms. It's a very active research area. Okay, so I will finish here. I just mentioned that I presented you one of my favorites research problem with an advantage, provable advantage over classical computer, so matrix multiplication, system of linear equations, also quantum simulations for chemistry, quantum optimization, and quantum algorithm for string problems. And I will finish by mentioning two pressing questions. So in my opinion, the most important open question is to find more application of quantum computer, especially more exponential speedups. This is really crucial for the future of quantum computing. And another interesting research direction is to try to build theoretical foundations for the advantage of quantum heuristic algorithms. Okay, thank you for your attention.